now come to section 5 of unit 3. Let's look at the section objectives. By the end of the section, you should be able to 1. Determine whether or not the inverse of a matrix exists. 2. Find the inverse of a given matrix where the inverse exists. Let's look at how to find the inverse of a 2 by 2 matrix. And we know that a matrix that is multiplied by its inverse will give the identity matrix. A superscript negative 1 is used to denote the inverse of a matrix A. So let the inverse of the matrix A is equal to A, B, C, D. And the matrix A is 2, 3, 4, 5. Since these two matrices are 2 by 2 matrices, the identity matrix would surely be 1, 0, 0, 1. So let's consider the equation A times A inverse is equal to the identity matrix. Then we replace the matrix A by 2, 3, 4, 5. Then we bring the inverse A, B, C, D. Then this should be equal to the identity matrix, which is 1, 0, 0, 1. So we will multiply the left side of this equation, and by what we have learned, this will give us 2A plus 3C, 2B plus 3D, 4A plus 5C, 4B plus 5D, and that should be equal to 1, 0, 0, 1. Then using equal matrices principle, we'll compare the entries of the elements of the matrix. So the first entry, 2A plus 3C, will be equal to 1. The second entry, 2B plus 3D, will be equal to 0. The third entry, 4A plus 5C, will be equal to 0. And then the last entry, 4B plus 5D, is equal to 1. I believe you can solve these 4 equations simultaneously and get the solution. Let's work on it and compare our answer to the next answer that we will get. Let's now solve the 4 equations simultaneously. So we will first consider equations 1 and 3. And solving them simultaneously, we will arrive at C to be 2 and A to be negative 5 out of 2. Also, we will solve equations 2 and 4 simultaneously, and that will give us D to be negative 1 and B to be 3 out of 2. So therefore, A inverse, which is equal to AB CD, becomes negative 5 out of 2, 3 out of 2, 2, and negative 1. We can factor 1/2 out. Then we will have negative 5, 3, 4, negative 2. I hope your answer is the same as the answer we have here. Let's now look at the inverse of a 3 by 3 matrix. So given the example, find the inverse of B is equal to 1, negative 1, 2, negative 3, 1, 3, negative 1. As usual, we'll assume the inverse of the matrix B to A, B, C, D, E, F, G, H, I. Then the matrix times its inverse will give us the identity matrix. And this is what we have represented as 1, negative 1, 2, negative 3, 1, 2, 3, negative times the inverse A, B, C, D, E, F, G, H, I. And since this is a 3 by 3, its identity matrix will be 1, 0, 0, 0, 1, 0, 0, 0, 1. We continue and multiply the matrices, and then we have A minus D plus 2G as the first entry, B minus E plus 2H the second entry, C minus F plus 2I. That gives us row 1. Then row 2 is negative 3A plus D plus 2G, negative 3B plus E plus 2, negative 3C plus F plus 2I. Then row 3 is 3A minus 2D minus G, 3B minus 2E minus H, 3C minus 2F minus I. And that should be equal to the identity matrix. Then, using the equal matrices principle, we will say that A minus D plus 2G will be equal to 1, B minus E plus 2H will be 0, C minus F plus 2I will be 0. So we form all the equations. Then, comparing the elements of the equal matrices, 3A can give us 2D plus G, and A minus D plus 2G will be 1. When we combine these two equations, we have 7G minus D to be 3, and also we have G minus D to be 0, implying that 7D minus D will be 3, and so D will be 1 out of 2, G will be 1 out of 2, and A will also be 1 out of 2. Again, let's pick the two equations. E is equal to B plus 2A and E minus 3B plus 2H is equal to 1. When we combine these two equations, we will have 4H minus 2B is equal to 1. But we know also that B is equal to 5H. And so by way of substitution, we have 4H minus 2 into bracket 5H is equal to 1. And simplifying, we have H to be negative 1 out of 6, B to be negative 5 out of 6, and E to be negative 7 out of 6. Similarly, we'll consider the remaining two equations. C is equal to F minus 2I, and 3C minus 2F minus I is equal to 1. When we combine these two equations, we'll have F minus 7I is equal to 1. Now, we know that 4 is equal to 4. We know that F is equal to 4I. And so, by way of substitution, we have I to be 1 out of 3, F to be negative 4 out of 3, and then C to be negative 2 out of 3. We can now put our answers together to have the inverse of B as 1 out of 2, negative 5 out of 6, negative 2 out of 3, 1 out of 2, negative 7 out of 6, negative 4 out of 3, 1 out of 2, negative 1 out of 6, negative 1 out of 3. Let's now look at how to find the inverse of a matrix of any size. To do this, you go through the following steps. Step 1. Find the determinant of the given matrix, say matrix A. Step 2. Find the cofactors of all the elements in A and use that to find a new matrix. Step 3. You now quote the formula and use it to find the inverse. And the formula is A inverse is equal to the transpose of the matrix of the cofactors divided by the determinant of the given matrix. So we will look at an example to illustrate this. Let's look at an example. Find the inverse of the matrix B is equal to 1, negative 1, 2, negative 3, 1, 2, 3, negative 2. So we'll find the determinant of this matrix. And the determinant is 1 into bracket negative 1 minus negative 4, then minus negative 1 into bracket 3 minus 6, then plus 2 into bracket 6 minus 3. Then when we simplify it, we'll get 3 minus 3 plus 6. And so the determinant of B becomes 6. Having gotten the determinant of the matrix B, the next thing we do is to find the matrix of the minus. And to find the matrix of the minus, we consider the first entry. We suppress each row and suppress its column. Then whatever is left forms a 2 by 2 matrix. We go to the second entry. We suppress its row, suppress its column. Whatever is left gives you a 2 by 2 matrix. We go to the third entry. Suppress its row, suppress its column. Whatever is left forms a 2 by 2 matrix. So we do this for all the 9 entries. And so the 2 by 2 matrices that we have, we find their determinants. And the determinants will form a new matrix. In forming the new matrix, we are guided by the operational symbols. The first one is positive. The second one is negative. The third one positive for first row. Row 2, we have negative, positive, negative. Row 3, positive, negative, positive. So we apply these operational symbols to the answers that we have. Now, as we apply the operational symbols to the matrix of the minors that we have previously, then we will have the matrix of the cofactors, which is 3, 3, 3. You remember in the minors, the 3 in the middle was negative, so it has become positive. Then we have negative 5, negative 7, negative 1. Then we also have negative 4, negative 8, negative 2. Then we are going to transpose it to have the matrix of the transpose cofactors. Then we have 3, negative 5, negative 4. That means that row 1 becomes column 1, row 2 becomes column 2, row 3 becomes column 3. So the first row, 3, negative 5, negative 4. The second row, 3, negative 7, negative 8. The third row, 3, negative 1, negative 2. We now put it into the formula which says that the inverse is the transpose of the cofactors over the determinant. And so when you do that, you have 1 out of 6. Then 3, negative 5, negative 4. 3, negative 7, negative 8. And 3, negative 1, negative 2.